AC is alternating current, which means that the voltage changes its magnitude periodically. So like, for example, if we were to draw the waveform of AC, it usually looks something like that. It's a sinusoidal waveform, where this is representing time and this is representing either your voltage or your current. Okay, that is AC voltage. Over time, the value or the magnitude of your voltage increases and decreases and goes negative depending on how much time has passed. This is alternating current. Whereas in DC, over time, the value of your voltage or your current is constant. Yeah, it has a constant magnitude that does not change. I'm sure we're all familiar with this. DC current is the stuff that is used in batteries, the stuff that comes out of your phone charger, laptop charger, and so on and so forth. AC current is what is available in sockets in any building that is supplied by Kenya Power, right? In Kenya, AC voltage is supplied at 50 hertz. What does that mean? That this cycle from going from low to high to low again, negative and up to the origin, this cycle repeats itself 50 times per second. I'm sure you're all aware of that. So the wavelength is 1/50, which is 0.02 seconds. So 50 times every second, it will go through this cycle of peak maximum, peak minimum, and back to zero. Okay. This has various advantages in that for AC, you have less complex generators. Generators in their nature, which we will talk about in the next lecture, are such that they are created generally by rotating a magnetic field within current carrying conductors. So you use a force, whether mechanical or some kind of other movement, that rotates the field within a set of conductors. If you need to change it to DC, you require the use of inverters and rectifiers. So the voltage that comes out of your generator is AC, then it needs to be rectified. The process of changing AC into DC is called rectification. And the process of changing DC into AC is called inversion. At the same time, one of the disadvantages of DC is that there is a limit in the size of generator. Because of the need for this process of rectification, the amount of power that can be generated directly into DC has a limit on its practical size. So that's a brief introduction into what we will be looking into. So let's continue straight on with sources of energy. So the main sources of energy are those which we have listed there. I've already mentioned renewable sources or green energy. These forms of energy are those that are readily available without the burning of fossil fuels. Fuels and thermals, this is diesel and so on and so forth, that kind of generator. And then we have nuclear, which makes use of the power of the atom to directly generate energy or heat. So those are the forms of energy. Now let's look at, when you have these forms of energy, how do you convert them into electricity? So let's start with hydroelectric power plants. So in Kenya, this is one of the most common. It used to be the most common form of power generation. However, this has now been overtaken by geothermal, which we will look at shortly. But in principle, in general, what would happen with a hydroelectric plant is that you have a reservoir at a height above the power plant where you want to generate. Your powerhouse is where you have your generator and your turbine. So there is a height difference between the water level of the reservoir and the water level of your powerhouse. Okay, so you have what you call a head. Right? Now, because of that, anywhere where you have water at a height, it tends to flow towards the lower altitude, the lower level. So that is what all these structures are for. So you have your reservoir blocked by a dam so that you have millions of liters of water being preserved, ready for conversion into electric power. So this has the potential energy, which we will make use of down here as rotational energy or as kinetic energy of the water moving through. So straight away, the water can be accessed through a pressure channel. Usually this is underground. You can see this is the ground that is there. So your pressure channel is just a way through which the water will flow in that direction, and you have a valve house. So the work of the valve house is to regulate the amount of water that will now flow down to your powerhouse. The valve literally has valves inside, and it determines how much of the water will be there. The more water that you allow through, the more energy that is being allowed through. So these valves regulate the flow of water. Then you have your penstock, sometimes called the race channel. The idea of this is it is a very smooth, it provides a smooth flow of the water and reduces the turbulent flow of the water, so that by the time it is reaching the powerhouse, it is at a good velocity and you can make maximum use of that water flow to turn the turbine. So the turbine is essentially a water wheel inside your powerhouse that is rotated by the flow of water. The water flows and turns a water wheel. It can be as simple as something like that, mounted on a shaft with a number of scoops, so on, so that you have your wheel would move in that direction, and you have your jet of water now from the penstock hitting your water wheel and turning it in the direction that is free. So now this water wheel or this turbine is then connected to a generator, or what we call an alternator. This is now an electric device which, by rotation, once you have that rotation going on, the shaft is connected through and you have your electrical machine inside there, which once rotated through a mechanism we will talk about in the next lecture, once it is rotated, it creates three-phase power that you can now make use of. So now the three cables that we usually see all over, the country is now able to be taken off from the hydroelectric power that you have. So straight away, because this is a very practical approach, let's look at an example. So a hydroelectric station is supplied from a reservoir with a capacity of 5 times 10 to the power of 6 cubic meters. So these are millions of cubic meters that you have in a reservoir at a head of 200 meters. That is the gap between the power station and the water level is 200 meters. Find the total energy available in kilowatt hours if the overall efficiency is 75%. So here we are saying that our hydroelectric power station can only convert 75% of the potential energy that is stored in your reservoir. So the reservoir has 5 million liters, 5 million cubic meters of water. Yeah, this reservoir that we talked about here. So that has 5 million cubic meters, and the head which we have here is 200 meters. So how much energy can we convert? The potential energy that is available in the water, how is it converted? We have the amount of water, or the weight of the water is what gives you the potential energy. So what is the weight? It is equal to volume times density. So what is the volume of water? We've already been told it's 5 times 10 to the power 6 cubic meters. The density of water is 1000 kilograms per cubic meter. Yeah, 1 ton per cubic meter, times now the weight, which is G, 9.81 newtons. So 5 times 10 to the power 6 times 1000 times 9.81. That gives us 4.905 times 10 to the power 10 newtons of weight. That is a force that is acting down. This is what is available to us. Now the electrical energy will be given by the weight, W, times the head, which was 200 meters, times your efficiency. which we said was 75. So we simply multiply all those together times 10 to the power 10 times 200 times 0.75. Like those 4.905 times 200 times 0.75, and you get 7.3575 times 10 to the power 12. Now these are what you call, these are units of watt seconds, which are similar to Newton meters, because we are multiplying newtons times the meters. Now, in order for us to get it in kilowatt hours, which is what we were asking for here, you then need to divide by 10 to the power 12. You divide by 3,600 seconds in an hour times 1,000 kilowatt hours to make it into kilo. And that gives you 2,043,750 kilowatt hours, right? So this essentially is the amount of energy that you can have in a whole 5 million cubic meters reservoir of water. So when you have 2 million kilowatt hours, a kilowatt hour is a unit. Those of you who have experienced prepaid meters, 1 unit is, the amount of power that you can power a bulb for like 24 hours, the old school incandescent one. So you can imagine 2 million kilowatt hours is quite a large amount of energy that is available for use. So hydroelectric power is a form of energy where we can have quite a useful amount of power. Steam power plants, this looks a bit complicated, but essentially it has 6 main components, which I will label here. So this is called coal and ash handling. Steam generating plant is all this section. And then we have a system here called feed water. And then we have down here, this is cooling. This part here is the turbine. And then finally, the electrical. So let's look at what we are doing here. These kinds of power plants, steam power plants, essentially what they do is they make use of steam to generate power. So what you will have is you have some kind of fuel which is used to generate steam, which is then used to turn a turbine, which is then used to turn what we call an alternator or the generator itself. Okay, so all forms of steam power plants have this basic design. You have a fuel that is either burned or generates some kind of heat, which now boils water and creates steam at a high temperature. Then the steam has a kinetic energy, which turns the turbine, and that has mechanical energy, which then turns the alternator, and then you have electrical energy as the final output. So you have your fuel, which is chemical energy or potential energy or whatever other form of energy, turning into heat either by burning or directly in its own nature due to a chemical reaction. And then it makes use of working fluid of steam to turn the turbine and the generator. So essentially what we have here is now a coal and ash system, whereby this is the fuel that is being used. So the fuel that is here, you have coal being stored and handled, powering a boiler, and then you have ash as the waste product coming out. Then you have the steam generation. So the boiler, which generates the heat that now goes into the superheater, and through various processes, the economizer, air heater, and so on and so forth, creates steam that is now pushed across. So the steam goes across to the turbine and it turns the turbine. So you have rotation of the turbine, which in turn is coupled to the alternator. So you have fuel into a boiler, the boiler has heat, which then converts some form of working fluid, in our case water, into steam. Steam, because of its nature, can then turn the turbine. The valve here is there to regulate the quantity of steam that goes to the turbine. The rest of the parts of the plant, feed water is about pumping water into the boiler. So it is the supply of water that will be heated and eventually go into the boiler. And cooling is kind of regenerating. You are trying to recirculate the energy that we have from the waste, either the waste energy, you're trying to make use of it, or you're trying to make use of the steam that is coming off of the waste. So like once steam has passed through the turbine, it goes to the condenser and can be condensed back into water. So from there, your turbine turns the alternator, and the alternator, of course, converts the mechanical energy into electrical energy. And these are now the cables that you have coming off. So now you have finally reached electrical energy. But basically, the next few types of power plant that we look at are this form. You will generally have steam power plants turning a turbine which turns an alternator. Okay, so this first one is a coal-fired steam plant. The next kind of plant that we can look at is nuclear. So a nuclear power plant is a similar sort of plant. Make sure you note that we are using steam once again. We have the same valve, the same turbine, the same alternator. So this is essentially a steam power plant. The only difference is that you're making use of nuclear materials or nuclear power to create the heat that we are talking about. So this heat. And in this case, there's a primary working fluid and a secondary one. The primary one is the hot metal that is passed through a heat exchanger. You do not heat the water directly with the nuclear reactor. You have a hot metal, sodium or whatever it is, that is literally melted, and that becomes the means by which you transfer the energy. So there are two stages. There is the first stage of heating, then the second stage of boiling. So let's make use of that principle. So what is the power output of that particular type of material or that type of power plant? In this particular case, now this is what we are talking about, radioactivity. So you have 2 kilograms of fuel. This is uranium, the number and the weight. So it's uranium-92 with a weight of 235. So this particular amount of fuel, that 2 kg, is being made use of over a period of 30 days. And these are now the details that we make use of. Okay, so I'll take you through. The number of atoms in your 2 kgs of fuel, yeah, remember this is a tiny amount of fuel, will be given by, you have 2 kgs divided by that atomic weight, which is 235, times Avogadro's number, which is at 6.023 times 10 to the power 26. Okay, where's our calculator? So 2 times 6.023 times 10 to the power 26 divided by 235 is given, then becomes, so you have this many atoms that are available, to produce our electricity. Yeah. Now, the period of fission, we call it fission, that nuclear reaction, is 30 days. So the rate, the number of fissions that you have depends on the number of atoms that are available. Each of these atoms is a potential fission that can take place. Now, over 30 days, you have 5.12 times 10 to the power 24 over 30 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And that will give us, divided by 30 times 24 times 60 times 60, which then gives us 1.9773 times 10 to the power 18. That's the number of fissions that we can have. 1.977 times 10 to the power 18 fissions. Okay. Now, in each fission, how much energy are we releasing? This is the question that you had asked. Okay, where is this energy coming from? So this number of atoms splitting, yeah, the amount of energy that they produce is given by 200 MeV. So MeV is the available energy in each fission, okay, times the joules, 1.6 joules, which is here. 1 MeV has 1.6 times 10 to the power minus 19 joules. Reason being, we need to convert from MeV, which is an atomic form of energy, into joules, which is now the energy that we measure in electricity. So times 10 to the power minus 19 joules. So 200, that is mega, times 1.6 exponential minus 19 joules. That gives us 3.2 times 10 to the power minus 11. In each of these fissions, we have that amount of energy being generated. So when we combine the two, the energy released per second, which is this, and the fissions that we have, the number of fissions, we then have the power is given by 3.2 times 10 to the power minus 11 times 1.977 times 10 to the power 18. So the amount of power that is available, that is the energy per second, yeah, because power is energy per second. So it is 3.2 times 10 to the power minus 11 times 1.977 exponential 18. So this is the power that we have. That is 63264,000 watts, which is given by 63 point, let's say 3 megawatts. Geothermal power plants look like that. So essentially, remember we talked of steam power plants running a turbine and then a generator, and then your load. That is just a representation of the load. In the case of geothermal power, you have the steam coming directly from the Earth's own energy. The energy is taken from the crust of the Earth, the Earth's crust. We all know that in certain areas, like for example in the Rift Valley, where there are geological characteristics that hotter parts of the Earth that are below the Earth's crust tend to flow upwards and they are near the surface. And because of this, we can make use of that heat to either directly or indirectly generate power. So when you directly generate power, this is called dry steam generation, which is what we have here. What we do is engineers will dig a well, essentially like a borehole, into the ground, into an area where you have trapped water that has been superheated already by the geological activity in the Earth's crust, and it is already directly in the form of steam. So essentially what you do is you've dug that borehole, and instead of water, you have superheated steam coming out, which is what you see here. And that steam directly powers a turbine, and it powers the generator or alternator, and it is taken off as power. That is dry steam. In certain cases, you have the same geological formations. However, you do not have steam in itself. So what you would do is you have to dig an additional well, which is the injection well, and you supply or you pump down water, which is then superheated into steam, and you tap off the same steam to power your turbine. So that is indirect steam. Another form is what we call flash steam. So flash steam is whereby the steam is not superheated. So it is not dry steam. It has an element of water in it. So it needs to first be separated off at the point where it has reached the surface, and it becomes flash steam because it expands out, and that is what powers your turbine. And we have certain other types of turbines, like a binary turbine, whereby the injection, the water that you inject in is not enough in itself to turn the turbine. So you would have water, if this is the Earth's crust, so you'd have pumped water going in, it is heated, and then it is taken off as heated water or steam, and then it passes through an exchanger, which then in turn powers or provides the steam that actually powers your turbine and consequently your generator or alternator. So this is called a binary geothermal power plant. Now, unfortunately,